have experience in doing the cleanup talk, and so I'll give it what I plan to promise to talk about, which probably won't be all that interesting because it got a little bit specialized. But then I thought I would say something about what I got out of this conference to help stimulate the discussion. So a little bit of an overview. This is, I think you already know. The history of this subject goes back a long ways. Let me see if I can get this. Yeah. So about 50 years is for me anyway. But the subject is about 10 years more. So at the time, early time when the subject started, when graphene was first discovered, there was nobody working in the field. So the work went almost unnoticed. And even the author mostly didn't notice it. I'll make a comment about that. And then we went through all these other topics, intercalation compounds that was discussed a number of times, fullerenes, nanotubes. During this period, we had a lot of people that joined the field. It got very, very exciting, and lots of people came in on the nanotube period in about 1995. And a big community was built up that understood something about linear E versus K. They, of course, didn't have graphene, but it was in their minds they had graphene. So that was going on in this period, and then the big paper came in 2004, and this field just exploded. And now we have approximately, what is it, 1,000 papers per year? More? 4,000 papers a year? Thank you. It's a huge number. Nobody can read so many, or maybe Andre can, but the rest of us probably can't keep up with it. So it's really a challenge. But it's nice to be, to find, for a person working in a field when you started, there was nothing there, and then we have so much interest. It's quite amazing. So I wanted to focus on the graphene, but I'll refer to a little bit about Raman scattering because that wasn't really discussed. So that was my topic because I'm the only one really talking about that in a more detailed way. So that's what I'll do. So we go back to the Wallace paper, and that was 1947. So that was roughly 10 years before I got into the business. And so when I was a very young researcher, my first independent career thing, I was told I couldn't work in what I had been working before, which is superconductivity, so I had to switch fields. And people were doing all kind of magneto-optics at that time, and I had access to high magnetic fields right where I was working. So that seemed like a good thing to do. And that is the direction I took. But everybody was working on semiconductors, and one semiconductor seemed rather similar to another semiconductor, especially there were 3,5 compounds, and people weren't making very good 2,6 compounds yet. So the choice was not so great. So I decided that I'd like to do something really different, and I thought I would do carbon. And I didn't get a whole lot of support or interest in this. And that was quite all right because I thought it was interesting. And all you people that are here now, you think it's interesting too, so you agreed with me. So and the field was set for me at that time to enter. We had a theory from my classmate, Joel McClure. We went to graduate school together. And he had worked out the E versus K for graphite. And we had it only in 2D for 2 dimensions by Wallace, and he made it in 3 dimensions, and I needed it in 3 dimensions. That was the paper in 1957, and in 1962, when I sort of entered the fray, he finished his paper on the magnetic field dependence. So he was just ready for me. And 1960 was also a celebrated year because that was the year that HOPG appeared here in London in Imperial College. And so I went to visit Imperial College. I gave a lecture there and told them that they started graphene in a way. But that is in fact the case. So I was able to get a sample that I could have an orbit, a cyclotron orbit, large enough in the sample so I wasn't getting scattered by the boundaries of the sample. So I had a theory and I had a sample, so it was time to get to work. So that's a history. I'm not sure that you all know about that, but that's how I got started in the business. What I'm going to talk about today, because that's what I promised to talk about, was how we use Raman spectroscopy. And as you can see here, there are all kinds of peaks in the spectrum. And I threw in the spectrum for nanotubes so you could see the radial breathing mode, because there's been so much written about that in the last 10 years or so, 15 years. But the main thing for graphene is the G-band, where the two atoms, carbon atoms, are vibrating against each other. And we have one layer and then a second layer, and that makes the unit cell, whether you have graphene or graphite. It's almost the same. So there's a great deal of similarity between graphite and graphene. So, and then there are a few other features. When you go to a conference, in graphene, you hear about the G-band, and then you hear about this G prime band, and I'll talk about it. It's sometimes called the 2D band. The 2D band is actually something a little different from the G prime band. I'm not going to get into this because this gets into some difficulties. It takes too much time, and I'm not going to deal with that. But I would like to speak about some other features. Between the G band and this G prime band, there's some scattering. And this M band hasn't been discussed very much. One of my Cromie students, Victor Brar, when he was an undergraduate at MIT, actually worked on this thing with me. And but for this occasion, we have some more work done with the people from Singapore. So that's developing. And Andrea Ferrari has done something recently on this very low frequency regime at less than 50 wave numbers. And I don't have his view graphs, and I haven't seen his paper yet. I don't know if it's published, but that's a new result that we'll be looking for in the next few months when it gets published, because that's a new feature in the spectrum that we've been waiting for a long time. So this is, even though this is like many things we heard at this conference, part of this field is quite old, but with the reinvigoration that came with the discovery of single-layer graphene, the field was invigorated, and some of these old traditional areas that we've been working on for years are now a little different, because we started thinking about this much more seriously, and we have results that we didn't have before. And that will be the gist of my discussion for you today. So a little bit on graphene with a review. So this is the 1962 paper of Burham, and I went to a couple of conferences, and people were questioning whether this was really a correct result. So I met Hans-Peter Burham in 1977 when we had the first intercalation compound conference, and they had maybe 2 handfuls of people. It wasn't a very big conference because conferences were very small at that time. There weren't that many people working in physics, but he was there, and but he didn't talk about this. He was talking about very early work that he did in intercalation physics. He was one of the pioneers in that area. And from the period that I knew him, in the early 1970s, when that field started, until he retired, that he was making new materials and a lot of work in intercalation physics. Never once during all that time did he talk about graphene. But I did talk to him very recently, like the last half year, and I asked him what he thought about this paper. He's exactly the same age as I am. He retired maybe 10 or 15 years ago, and he doesn't travel, but he remembers this paper, and he says he sticks by it. So there you are. So it has about the synthesis of a single layer graphene, and he has a table that shows something about it. And he believes that he made graphene from graphene oxide, and some other people have been reproducing that work. I wanted to pass this on because there were some questions about this work, whether he believed in it, what happened to him, and so forth. Some people don't know this history. Okay, so here's graphene, and we've seen this picture many times. There's not much more to say. 2 atoms per unit cell. And the B atom can be in this position, or it can be in this one, or in this. So we have some choices, and we could make ABC stacks with different configurations. But the AB is the ground state, and that's what we normally have. That's ordinary Brunel graphite, and that's what we have a lot of data on. There's also the ABC version that has been known for many years, but there's almost no data in the literature on that. That's a very uncommon form, and there's very little work that has been done on it. And it's gotten interesting now that we have graphene, because we can make these different combinations, and maybe many more from the discussion that we had here. So that opens up another research field that we might be thinking about. Okay, so this you've heard, and so we have a single layer, and we have the linear E versus K, and we have bilayer very close to the Dirac point. We have a quadratic form, but when you look away from it, it doesn't look terribly different from this, and except that you have 2 layers rather than 1. I have a little more to say about that. So this is a picture of monolayer and graph. And 2 layers, and it was discussed numerous times. This is the famous paper that I think broke the field open, and after this came it started the 1,000 paper. Now we're up to, maybe we'll be up to 10,000 by the end of the decade. So anyway, the field took off after this point, the quantum Hall effect, integer 1 in graphene. It was different than gallium arsenide, so people got excited. Soon thereafter, there was Raman Spectra, and this was also taken by the Manchester group in conjunction with Cambridge. So this is Andre Ferrari's work. And we have known that for a long time that the second order effect, this G prime band, is very large compared to the first order. Usually in physics, the second order effects are second order, and they're small. That's why we call them second order. But we had this material, because of the linear E versus K, you have all K vectors in the Brouillon zone resonant in a sense. So you're always doing triple resonance. In general, for graphite, we have a double resonance effect that's responsible for this G prime process. I'll tell you that a little bit more about that later. But every possibility that you can have for the monolayer is resonant. So it gives you this huge signal at the second order effect. And the bilayer is also quite large, but it's much less than the monolayer. I have been waiting, I'll throw this out to people in the audience. I've been waiting for people to consider this system as a metrology system, because it is kind of simple, and in a way, everybody can reproduce it. And we could use, as Philip Kim in his talk was talking about doing the resistivity as a function of temperature and seeing what the power law and checking the old formulas that we have going back to ancient times. I believe that it is correct to say that until you did it for graphene, nobody checked the T to the 5th power that occurs in the resistivity. I don't know if you know that, but if you look in Kittel's, where he has all these curves superimposed, yes, they're all similar, but they're not T to the 5th. So it's really great that you could show that result.
My PhD.
You did T to the 5th?
Yeah.
Oh, okay, but Catel's picture is not T to the fifth.
Yeah.
Okay, all right. So you did that, and I didn't know that. Okay, I apologize to you.
It was so boring.
Well, it's we have to advance the concepts of physics too, even if they're boring. So this is the process
He
that's.
said his thesis was boring. Not the talk is boring, his thesis is boring.
Well, I'm happy. I didn't follow that because I kind of stopped teaching at one point. So anyway, I'm going to explain what happens with the G prime band because we'll be using that in the talk. So this is the second order process. A photon comes in, it excites an electron from the conduction band to the valence, from the valence band to the conduction band, leaving a hole behind. So we have an electron-hole pair. So that makes a neutral system. One of the new things that I learned that's just coming up now, but I didn't hear it at this conference, but we're supposed to talk about what's happening in graphene, is now people are not only exciting electron and hole, but they make an ion charge. So you have two holes and one electron, and they call that a trion, and that has a different spectrum. But I didn't hear anything about that here. I think that's an interesting new development in this field. So anyway, let's go back to this story. So we have the electron excited, hole is left behind, the excited electron gets scattered, and it scatters from the K to the K point, which is essentially a equivalent point, but except that there's time reversal symmetry between the two. But when it gets to here with the scattering process, it emits the phonons in the Stokes process, so it loses a little bit of energy, and then it comes back here and loses a little bit more energy, and then it recombines. So this is a two-phonon process. There are no elastic events, as stated. If the elastic events happen as they do in the D band, then this would be 2D. But those elastic events, well, they could be there, but that's energetically not favorable. So that's the difference between 2D and G prime, if you really want to be fussy about that. So now we go with different photon energies. And so with different photon energies, we'll be having a smaller Q factor, and that means that the phonon will have less energy. So because of that, it will be shifted. So you have a dispersion relation. G prime is always a dispersive feature. And now if I come in with red light here, it's even a smaller wave vector. And so you could see that the G prime band has a very large shift, but I'm going to show you some others that have even more shifts later on, which is very unusual in second order processes. So the shift here is 100 wave numbers per EV. That's very large for Raman scattering. Because of linear E versus K, every one of these processes is resonant because we're going from a real state to another real state. We scatter to a real state, we come back to a real state, and then we recombine to a real state. So everything is real states, and that's the reason for this huge intensity. In the Raman effect, you often make the transition to a virtual state, and therefore the probabilities are very much reduced. So that makes this a line shape very unusual in physics. I don't know of any system that's like this. This is a unique system. So now that was the first order effect. So that's one layer graphene. But now if you have bilayer graphene, and we have a lot of papers in bilayer graphene, so we should say something about that. So the photon can come in and make the excitation I've described before for the G prime process from the lowest energy band, that's this one here. And so that we go here, back and forth, and then I call that P11. And the total energy of the two phonons that are created will be up here. So this is P11. So that's 1 point for some energy of excitation. Since everything is resonant, we have a choice of lots of points to do here, so we can populate this whole line. But instead of doing the first level, I could do the second level. So here's it starting in the second level, going to the second level, scattering to the second level, everything to back and forth second level. That's P22, and that's over here. But I don't have to do that. I can go to the, here I can make a transition here to the from the first level to the second level, and then come back and I can, this one is from the first level to the first level. Then I go to the second level here and come back on the second level and find myself a hole to go to. And so that makes the cross term P12, et cetera. So that's where all this comes about. And since the phonon, it has a different wave vector, it'll have a different energy, and you could separate. It's separated by just very few small energy, just a couple of millivolts. But you can certainly resolve that. And if you're looking at a whole bundle of a whole bunch of bilayer, you get a spectrum that looks like this. So not the individual peaks are not resolved. The line width is greater, so they overlap, and you get overlap energy. But it has a certain line shape, and that was what has been one way that people have quickly identified this as bilayer and not monolayer. Monolayer has this huge single peak, and this one has a much broader peak. Now I'm going to show you something new, a new feature. So we have yet another thing that we could look at, and then I'll go on to talk about other subjects. So this is work done in collaboration with a group of young people in Singapore. And so they had a sample, and the sample is kind of nice. Maybe it has some deficiencies because it has a lot of different regimes here. But they have a region that's one layer, and they have another region that's bilayer, and 3, 4, etc. And it's a pretty big sample. It's some microns, so the optical beam can be housed in one of these regions. And so they did a scan to find out what's in the sample, and then they came back, doing the kind of thing that you've heard here several times of seeing what the absorption is at different spots. You can sort of monitor where you are. And what we do in these kinds of samples, we put a fiducial marks on the substrate, so we can always come back to exactly the same place on the sample and repeat and do the spectrum repeatedly on the same point. So that's the way the experiment is done. And this is usual, you know this. So this is the G band. It's discussed many times, and that's G prime. I discussed that as well. And in single layer, it's very, very big. And then we have another region in here that you don't see a whole lot. But if you are very persistent and you look in here, you can identify Victor Brahe's M bands. I think Michael Crummy will be happy to see his students' M bands. And then I'll show you all the stuff we missed because we didn't maybe spend enough time looking for all these other little features. So this is the place that we're going to look now. And so this is the region here between roughly 1750 wave numbers and 2100, 2200, where there are other features. If you look carefully and spend a lot of time looking, you will see more things. So the first part I'm going to show you is what happens between 1700 and 1800. And this is a region of the spectrum that we had studied before with Victor Brahe. And at that time, we identified two regions, M minus and M plus. And when you look at this, we saw this looking like the letter M. Can you see something that looks a little bit like? We thought it looked like letter M, so we call that the M band. We didn't have M band in graphene before, so that's what we called it. But then when you look at it a little bit more carefully, you notice that this has a non-Lorentzian line shape. And this one is mostly Lawrencian, but this one has a weird line shape. And if you look at all the places in the sample, from the thickness measurements, et cetera, there is no signal whatsoever for the monolayer. It's absent. And you begin to get something in the bilayer, and then you get some more. And if you sort of look at the features, well, this is maybe the most interesting, so you have maybe 3 features. And if you think about this as 3 Lawrencians and you apply that to the whole series, then you get something that I'm going to show you in the next view graph. So I'm going to show you a little bit of results for what happens in this region where the M band occurs, and that one we knew something about. But then I'm going to show you something about this region that as far as I know, nobody has studied before. And maybe we should go back and look at all different kinds of regions, because maybe there are more things like this that we've missed because we haven't looked carefully enough. So I guess last night we had a philosophical discussion about science. Some of you were present. And somebody was criticizing the science community that we don't do careful work. And I think that in defense of the science community, I think that the first thing that you do when you do science is you do what's apparent and what's easy and accessible, and you have a chance of understanding it. And then maybe something gets more interesting, and you come back and see if there's maybe more to it. And I think that the R to the 5th dependence of the low temperature resistivity is maybe something in that department that we wanted to get it right, and it was wrong for many years. And I think there are a number of other things that came up at this conference that are also in this category that people call boring, but they've been wrong not quite right in the literature for a long time. And now with graphene, we can straighten them out. So I think that we should say that that's a positive thing that we can do. We'd like to have everything right. And sometimes getting everything right is difficult. But if now we have material that is enabled, maybe we should go ahead and do it. Okay, end of philosophical comments from last night. Well, I think as the last speaker, and I was told I was supposed to summarize what we learned at this conference, and that was one thing I learned from the conference, is that the people in the UK like to have philosophical conversations. So and now I am here talking about the M band, and I'm going to show you in a few view graphs how we did a little more careful study of the M bands. So one layered has nothing, so it doesn't appear here. It's absent. So now we have to have a theory to explain that why there's no M band in monolayer graphene. But in bilayer graphene, because looking at all the different number of layers, you have the idea that the lowest term here, this one here, should be a doublet. So, and you identify that as a doublet. It works rather well, and then you could follow all the components. And so then we have the second part of the doublet, and then we have this piece here. And usually when we do these kinds of things, we like to identify which phonons are involved. And the frequency for 2 out of these 3 work rather well with the M band, which is identified with this phonon. So you see that there are 3 acoustic phonons and 3 optical phonons. And there are 2 atoms per unit cell, so that all makes sense, right? That's elementary, boring physics, but we have to keep track of those things to make it right. And the outer plane, a very soft mode that comes in the C direction, we know almost nothing about. So even though it's boring, it's kind of interesting. And so we had some new insights about that feature from Andre Ferrari, but he's not here to give that talk, so, and I don't have his data, so that's coming up, and we'll read the Physical Review or Nature or ACS Nanoletters. I don't know where he's going to publish that. But that is the analog of what happens with the G-band. So anyway, the identification of this is twice this mode. So this mode comes roughly at 900, and but a little bit less, like 970, 870. That's a known mode. It's IR active. So we know that. We don't know from Raman spectroscopy because it's Raman forbidden, but it can show up if you have some kind of disorder or edge states or something. And it's a very weak feature. I was saying you have to really work at it to bring it out. So so that's the M band, and these two work with a combination of twice the M band, one for intra-valley scattering and the other one for inter-valley scattering. So intra-valley scattering, instead of going from K to K prime, you just stay on the same K or the same K prime, but you don't go between the valleys, and it takes less energy to do that. So they're a little bit shifted from each other, and that all works out in the energetics of it. And then we have another mode here, and so we made an identification of what that could be. And so the two TO modes that we have. But then we have a combination mode that we're going to identify with this lower frequency mode. So yeah, so the what's clicking for you is the OTO, and that's the infrared active mode. That's made a Raman active by having the small feature and probably some defects. So we have a symmetric and an anti-symmetric combination of the two vibrations. The vibrations are the same with respect to each other within the plane, but across the plane they have opposite phase, and that's shown on the top here. And that opposite phase introduces larger Q vectors, and that's why we have small frequency shift. So that's the explanation of that piece. Let's see what we have. And okay, so the three bits that we have here are the TO modes, the two of them, and then we have another piece that I'm going to bring in a little while, and that's this one here. That's a lowest one, LO plus ZA, and this is the frequency, the laser energy, where all these pictures were taken. So that will give you the identification of what it is, LO plus ZA. And now moving along here, let's see. Okay, now I'm going to go to the next little bit, which goes from 1850 or so to 2100. And now we can have something happening for the monolayer. You see there's some peaks, and so what are they all about? And you could follow those peaks. They go not only for HOPG, you have them, but you have them very nicely for monolayer. It's very much more helpful than HOPG. And then you get what happens here as you go up the trail. And so now we have to do some identification of what these things might be. You see that they're all dispersive, and then, but there's, some of them are a little bit asymmetric, and you have to find some kind of identification what they are. So here are some possibilities that we came up with. So we have three different possibilities here, and I hope we have some, yes, we have some names for them. And so here's combination mode that works in frequency very nicely for this. So the ITA is this one here. That's the ITA. This is the outer plane mode, and then LA and TA, and then we make combinations with these guys, LO and TO. ITO is the in-plane optical. That's 1580. That's the one you know very well. G-band is what we call that. And So here are three, and then we had three from the from 1700 to 1800, and I believe I have all the identifications. There are 4 identifications for the higher frequencies and 3 for the lower, so there are 7 altogether. And there's another group in Clemson University that's done something very much like that. And they also have the same identification independently and for the same group of features. So if you sum up the story, there are a bunch of wiggles here, and they vary as the sample changes. Go from 1 layer to 7 layers. There's some small difference that hasn't been worked out in detail yet, but you see that where we're headed here. And there are some that show, say, this feature here, this M-band feature, and there are others that require that we have to go to 2-layer, bilayer, single layer doesn't have it, and if the 2 layers are incommensurate, you don't have it either. So you have to have A-B stacking and more than 1 layer. So that's what we've learned. Those are new results, and I don't know how interested you are in this, but I think that what we're going to see as a result of our discussion last night, plus other things happening in the field, that people will clean up all these little features. There are a whole bunch of features. There are combination modes of this sort. When we were studying fullerenes, we had 200 combination modes to put together. And you have a C60 molecule, you have a huge amount of symmetry, and they all seem to combine. And some were infrared active, some were Raman active. That didn't have much broken symmetry because the fullerenes are really very robust molecules. But here we can have vacancies, as we found out, and other kind of distractions. So this is to show you that how the M-band is a new thing, and we have to do more theory with that. Okay, a little bit now going back to nanotubes. Nanotubes are different from graphene, and we've been working on nanotubes maybe 10 more years than graphene, and the field is still active. How come? Maybe that field should have been dead by now, because usually 10 years is enough to exhaust any field. But the problem with nanotubes is, and why it's still active, and maybe will stay active for, I don't know if 10 years, because we have so many experts now from graphene that when they get tired of working on graphene, they may try to mop up the unfinished work in nanotubes. It's very easy for them because the physics is very similar. But there are many things in nanotubes that are still not understood. And why is that? And I'm going to try to say that because I think it might be interesting to this audience when they do something and they want to see how it is in nanotubes. So a nanotube is a rolled up sheet of graphene, and we can have a single sheet. And it was kind of funny that this whole thing was fantasized well before it was ever produced in the laboratory. And maybe it would not have been produced in the laboratory anywhere as quickly if it hadn't been fantasized. And the reason was that for various historical reasons I won't go into here, we were into the idea of predicting what the nanotube would be like if we could ever make it as just a Gedanken experiment. And the prediction was by 3 groups, and they came out at the same time. The papers were published in different journals around the world, different countries, at the same time, predicting that if we ever could make a single-wall nanotube, it would be either semiconducting or metallic. So that was 1992, and the first single-wall nanotubes were made in 1993, about half a year, 9 months after the first papers predicting them. How interesting would it be to make them if we could? So what's the reason for it? What's the physics behind that? So I'm going to go into that and try to explain that. So if you take a graphene sheet and you roll it up, then you have a very few atoms around the sheet, maybe 10. So that means you'll have 10 cutting lines. And so you have the graphene cones like this, but since you don't have all the states available, you only have 10 states to manufacture from this, and you have to space these cutting lines appropriately to satisfy quantum mechanics. As you put them in, and the geometry that goes into requiring how you put them in, a cutting line might cut through this Dirac point, or it might not. So it turns out that 1/3 of the cases will go through the Dirac point, and that will make a metallic nanotube, and the other 2/3 of the possible cases will not go through, so we'll have a semiconducting nanotube. And so that's just from the geometry of the triangular lattice. So that was predicted, and people didn't believe it, I must say that. And it really took until 1998, 6 years later, after the first papers were written, for people to say, yeah, we can have metallic and semiconducting nanotubes. Most of the people in this audience don't know that history, because when you joined this field, probably, it was all settled. And everybody, as soon as the experiment was done, showing that actually in the laboratory we could make them and had spectra, then it was all over. And so that's what happened starting in 1993. Okay. Anyway, for the nanotubes, we also have this radial breathing mode. And so that's where all the atoms in the tube are vibrating in a radial direction. And the frequency depends on the diameter. So that becomes identification of the nanotube diameter, and it's been used for that ever since. And also, we can, a little bit more indirectly, identify what the NM is by measuring, that is the chirality and both the chiral angle and the diameter of the nanotube, just from this frequency and the theory behind it. Then we have the longitudinal vibration associated with the G-band, and it has a transverse component. We mentioned that already. And then we have the second order feature, G prime, that I already mentioned. And then we have this M-band that's new, and we're just learning about it. And then we have this disorder-induced band here that shouldn't happen, but if you break symmetry, so we have a lot of symmetry breaking discussion at this conference, and that's one of the features, one of the early features that we used in carbon science to study disorder, breakdown of symmetry. We're getting more sophisticated, and I think in the last year, one of the things that I'm seeing is that we're not just satisfying that saying that we have a defect, but we want to know if it's a vacancy, if it's a divacancy, how the divacancy is ordered, if we have an edge. An edge is a discontinuity in the infinite lattice, so that can be treated as a defect, and it produces a discontinuity, and we can pick that up. So the radial breathing mode is here. And you can see it's at different frequencies, and that indicates that we have a different nanotube that's in resonance with a different diameter, so therefore a different frequency, and then we can get the NM values. So there are many ways now. There's Rayleigh scattering and other ways to determine NM, and I think the interesting thing that I've been picking up right this year, and is pretty new, is many labs are now doing multiple experiments to correlate information, either on structure, on electronic properties, optical properties, magnetic properties, whatever. And it used to be that when you published a paper, you would have one technique, But now, some of the really interesting work that I heard in the Bordeaux conference before coming here was of this two different kind of techniques. So I throw this out to you because not many people from this conference were also there, but I was. So I summarize a few things at this conference that I learned from them there. So the earliest work, like here, was done on bundles of tubes. And with bundles, you just get an ensemble information. That's the earliest work that we did. This very first paper, a historical one on first Raman in nanotubes, was 1997, and that was done on bundles. But it became obvious right after this experiment, we did another experiment to show that the spectrum looked very different from metallic than semiconducting tubes, and that meant that we really had to do this at the single nanotube level to be able to, in detail, understand what went with what. So this picture on the right is spectroscopy taken only on one tube, and so we have one semiconducting tube, and that's this one, and one metallic tube, that's over here. So this is the first paper on single wall spectroscopy in the nanotube department. But now people doing it with many other kind of techniques. It's not only Raman, it's many other things. So what's Raman spectroscopy good for? So this picture has a lot of people's work, and it shows, it allows you to distinguish between different kinds of carbon. So this is just maybe a little, not everybody realizes that diamond and graphite have very different spectra. So there they are. You can see frequencies are totally different, but they're all carbon. So sp square bonds and spq bonds, they have different separations, and they have different coupling. You know, one is planar bonds, and the other one is tetrahedral bonds. So it's obvious that they'll be very different, and so you see different spectra. But not only that, when you have different kinds of sp squared, so this is graphite, and this is single wall nanotube, and amorphous carbon, and everything looks very different, and that has to do with defects and many other issues. So we can use Raman spectroscopy to take other allotropic forms. A C12 and C13 that came up at this conference, you can tell them very, very well by Raman spectroscopy because the vibrational frequency of almost everything will depend on the mass of the atom, and C12 has a very different mass, and it's almost 10% different from C13. So it'll be way separated, and you can distinguish. So some of the experiments people were talking about here would be relatively easy to do. And there's one paper that we recently published, but I don't have the view graphs for it, where one layer is C12, and that's on a substrate, and then we have another one that's C13. Well, it's actually the other way around. The C13 is on the substrate, and the C12 is deposited on top. And we can study substrate effects directly, because one of them has a different, they show up differently in the spectrum, but the interaction is almost the same. So those kinds of experiments I throw out to you as being very relatively easy to do nowadays. It's easy to get isotopes, and they give you a lot of information. So that's an addenda to this. Some of the modes are dispersive, and that's what I have here to show you, that you can do studies here as a function of issues like size of a domain, and that changes the amount of D-band that you have. Or you could just do experiments to see what the dispersion is, to study what the wave vectors are. Because with Raman effect, you could measure phonons, and the phonons will be different in a second order process depending on what the photon energy is. So that's one thing that you can do easily. And this one I threw in here to show you that you could study issues like doping. So if you have an undoped sample, you get one kind of spectrum, a p-doped sample, and So the top one here is undoped, and then you have N-doped and P-doped. So the N-doped pushes the frequencies down to lower frequencies, and the P-dope pushes the frequencies up to higher frequencies. Same thing happens in intercalation compounds. So this is sort of general throughout the carbon literature. So if you know that, you can do a lot of things. You could study pressure dependence, and you could see here for different amounts of applied pressure, you get shifts. And so this is part of, so this is uniform squeezing. We had stretching mostly in the talks. You could do stretching here too, and that gives you something similar. Temperature effects, that's another thing. These frequencies, you change the separation by a little bit of the carbon-carbon distance, not very much is necessary, and you get big changes that you could see in the spectrum. So temperature-dependent phenomenon can be measured. You can measure equilibrium or lack of equilibrium between electrons and holes, because you could probe the phonons and then probe the electrons at the same time. The electrons come in terms of the wave vectors that are chosen, and the phonons come in by the phonon frequency. So on the very same shot, you can study electron-phonon interaction in this kind of way. And then we have edges. Edges represent a breakdown of symmetry. So group theory and symmetry tells you that if you're an internal point here, there should be no reason to have sort of infinite lattice, so you'd have no D-band, no disorder-induced band. But if you come over here close to an edge, this is an armchair edge, which we found out by doing Raman, then you get a big D-band signal. But symmetry tells you that the zigzag edge has a vanishing matrix element. So if the sample had been a really good sample with a perfect edge with no defects, then this signal here should have vanished. Well, it's pretty small, so that's the best at that time. This is pretty old work. It's 7 years old, and we make better edges now, but that's just to show you an idea about edges, how you could study them. So this is doping and defects. So if you add more a quantity of a dopant, you broaden the lines. So that's what's shown here. And then this is, well, donor and acceptors. This is mostly what I put together here to show you that doping and defects can be studied. And this is now size of samples, domain size. Grain boundaries, we saw a wonderful picture from Cornell. I think that was showing an individual grain boundary. We saw 5, 7 defects along the grain boundary, the boundary of the grain between two grains. I think was it you, Philip, that showed that? We saw that today. Somebody own up. Yes. Dr. Hong from Korea showed that. But I believe that picture was taken at Cornell. Was that right? Yeah, that's the one I know. That's a very beautiful picture. And so that shows us that we could understand what happens at the grain boundaries. And now we know exactly, so just a whole series of stone whale defects along the grain boundary. It's really a very beautiful, maybe we'll bring that again if anybody's interested in seeing that. I think we can learn a lot from that. And this is something new. It's submitted but not published. And this is electronic spin resonance, not spin resonance, electronic Raman scattering. So what is this effect? This effect has been seen in other systems, but this is the first time it's been seen in the carbon system. So a photon comes in, makes an electron-hole pair. Electron-hole pair can be generated for any different kind of wave vector. So that's the reason that you have this very broad band. It can be seen if you have a rather pure sample, so that the Fermi level goes here, because you have to go from an occupied state to an unoccupied state to excite this system. So if you dope the system, you'll kill this transition, because this is not that many MEVs, so you can quench it with moving the Fermi level. This is observed for metallic tubes, not for semiconducting tubes, so it's unique to that. That's the prediction, and that's the observation. So that's a new topic. Double wall tubes. I'm going to say something about that. This is sort of, to me, a little bit analogous to bilayer graphene, so I show a little bit about that. This will be very brief. Whereas single-wall nanotubes, there's a uniqueness. If you have the 6.5 tube, and you show the 6.5 tube, the Raman Spectra, and you do it in one lab and you do it in another lab, you get pretty much the same spectrum. But if you do a double-wall tube, that's not the case. And the reason for that is that if you take the two tubes, you could move them with respect to each other, so the hexagons, relative positions of the hexagons change, and then you could change the chirality this way. So you have two ways to alter this spectrum. So you get a range of values for any one tube. So be prepared for that. So at the conference in Bordeaux, they had Fen Wang, and he and his group have been working hard to get kind of a standard Katara plot for single-wall nanotubes. And once that's established, so if you have good data to send to him, he's putting everybody's data together and taking into account environmental effects and everything else, so that we get some metrology going. And he's the one that's really championed that program. So many of you know Fen Wang. He's a very able young professor at UC Berkeley. You might want to cooperate with him, because that would be very interesting. Now, with double-wall nanotubes, we have 4 different flavors that you can have, and the Katara plot was going to be different from all of them. So the situation gets a little bit more complicated, but Raman spectroscopy could be very useful for characterizing all of these different tubes. The bottom line is that the double-wall tubes do not quite behave. If you take a 6.5 tube, and it's a single-wall tube, and you put it inside a double-wall tube, its spectra will change, but not that much. It doesn't change so much that we lose identification. You can mostly identify it, but be aware that it may change even its identity in that part of the space where you have many tubes, a high density of tubes. That's large diameter tubes. So here's the double wall tubes here. So this is a bundle, and you see with the bundle, you have a mess. You have tubes that you can't identify exactly, so you never know which outside tube went with which inside tube. So really, spectroscopy is not possible. But if you do it at the single double-wall tube level, you can identify the various features. So I'm just showing you this to encourage you that if you want to do spectroscopy, you have to work at the single nanotube level. Okay, so that's enough said on that. And the spectrum for graphene and nanotubes is similar but not identical. So this is a topic that has to be researched, and I would say there's a little bit of work, but not a lot of work. So this is still something for a young person to take on. With the double wall tubes, you can be in a situation that the inner and outer tubes are resonant at different laser energies, like here. And working at the individual nanotube level is essential to separate all of that stuff. And so few labs do that now. And sometimes you're lucky, and with the same laser energy, you could see both the inner and outer tube. But that's unusual. But I show you sometimes you can be lucky. And now people are doing triple wall tubes. And then this has gotten interesting because people are interested in tri-layer graphene. So the correspondence, and you could see, I'll show you some spectrum where we were lucky and we managed, well, this is a triple wall tube you can see here. this is where the tube grows, and that's the 2 and 3. And so here's, it's sort of, it looks a little bit like a mess, but here's the radial breathing mode on the right, and this is the G band and D band region. You could see a lot of activity, but I think triple wall tubes we'll be able to separate out and see what the shifts are. But I'm not interested in doing more than 3. I think I'm going to stop at 3. I think 3 is about my limit. Just a couple of comments about ribbons. Ribbons are something, and edges are something that are unique to well, I don't know if they're unique to graphene, but they're part of graphene. And so there are the edges. And whereas nanotubes, they can have any chirality and any angle works with almost equal probability. I'm going to show you that the edges in graphene are very special. They're not like nanotubes at all. They have very great preferences. I was surprised by this myself, but I'll show you. So this one here, the edge is zigzag, and the edge here is armchair, and we label the ribbons in that way by the long edge. And you could say, in a sense, it would have been a little bit more symmetric if we had labeled them by the short edge, but that is the way we did it historically. I mean, I won't take the time to explain why that is, but that gives you more symmetry between nanotubes and ribbons. But historically, we didn't do it that way, and I think we better not change now, create too much confusion. We have enough confusion with G prime. I'm not looking forward to any more confusion. So here's armchair. You see, this is now no spin-orbit interaction. This is our 1996 paper, very ancient. But you have a ribbon with 4 rows of carbon atoms, so we call that n equals 4. Everybody uses that notation, and you can see that's a semiconductor, and n equals 5 is a zero gap, linear E versus K ribbon, and here now we have a semiconductor again. The zigzag is different. N4, 5, and 6 and anything has a high density of states at the Fermi level, and that makes that one quite reactive. So the chemistry is really quite different. And when we do experiments on these edges and folded edges and so forth, they really look different in the microscope. So we've gotten used to that. And the reason for it is this difference in density of states, which really pops out at you when you do the experiments. So Inoki, a long time ago, started making ribbons, and even before we knew how interesting they were. And so here's an ancient ribbon, 2004. It's off the page, but it is 2004. And so you could see this is 80 nanometers, and you could see that's very small compared to 80 nanometers. So you were in making quantum ribbons. And this is the heights. You could see that this piece here is 1 layer tall. So this is a monolayer ribbon. And this is just to show you that Raman spectroscopy satisfies the selection rules as it might. And so we have a ribbon sitting on graphite. So the upper frequency is graphite, and that's the substrate. The ribbon is this one, the lower frequency. Why is it lower? You put a laser on it, and it's a very tiny ribbon, and even if you put a small amount of energy, it gets hot, because the C-axis thermal conductivity is very poor. So it has very poor contact, so laser energy heats it. And so that's what produces the downshift. So we can tell them apart, which is nice. And then we do polarization experiment. That was predicted in 2003 to have a cosine square dependence. And the experiment gives cosine square dependence. So we were happy with that. And so this tells you we can understand a little bit about ribbons, identify them with Raman, and get some information. So other people have shown this view graph also. This is a 2004 paper that distinguishes the D-band itself. And the D-band has an elastic process in addition to the inelastic process. It makes a phonon, but it also has an elastic process. So 2D would have two elastic processes, but what people call the 2D usually has no elastic processes, so it gets a little bit confusing. It makes a small difference in the frequency, if you want to be technical about it. Okay, so this is now how to clean up the edges, and then I'll end. So we have a TEM microscope, and we put our little piece of graphene ribbon here, and we put electrodes across so we can make IV characteristics, and we can also do Joule heating. I just want to show you. So the ribbon that, this is a ribbon that was made in Mexico and Mauricio Terrones' group, and it's over here is the ribbon. They brought it to one of the meetings and showed me a picture of it, and I said, come to MIT, let's look at it. I think it'll be interesting. So we did, and so we did some Joule heating. This is the sample in the beginning. It's very, very disordered. There's no clear demarcation of where the edges are here at all. And then a little bit of Joule heating starts out linear I versus V, so that's no temperature, no heating. And then it gets nonlinear. And then at this point, the whole thing takes off, and it gets extremely nonlinear. And that's when you start having motion of ions. It's about 2,000 degrees up here. We put some little particles of platinum to measure what the temperature is. And I'll show you this in more amplification so you could see what was happening. And so you see that this is the ribbon that we start with. And after some Joule heating, this is SEM picture, so you could see low magnification. And here are a bunch of edges with about 20 layers. So they form arrays. That interests me. And the more you heat them, the more these arrays line up with a constant distance between them. And interestingly, the edges are almost entirely either zigzag or armchair edges, and we don't have anything in between. So that is very different from the situation of nanotubes, where all the NMs occur. So it'd be nice to have more data on that. The chiral ones are black, and you see very few chiral ones. And the probability of having the armchair and the zigzag is small because it's a very special orientation. But almost everything is armchair and zigzag. So, and that sort of thing doesn't happen with nanotubes. You know, we have 6.5 and 9.3 and everything else. But with graphene likes to have the high symmetry directions. And theory says that in equilibrium state, the armchairs should be more frequent, but when you do make them with Joule heating, the zigzags seem to be equally or more. So, and you can actually watch the motion of these junctions between the different kinds of edges, and we've been moving them and measuring the velocity motion and so on. So this is going back to yesterday when we ended our discussions. What's next? We've had graphite. We have intercalation compounds. Intercalation compounds have infiltrated graphene. People put stuff between the layers, and is very much related to the early work on intercalation compounds. And it's very interesting what happens with graphene, because you study the effect for bilayer, even single layer, that's sort of putting surface atoms on. And that field, I think, can become interesting again after not being too active for many years. And, well, we've had fullerenes now. Fullerenes are important in the energy business. And we have nanotubes, still going. And graphene has taken off. And what are we having next? Linear chains have been looked at, and that hasn't turned out to be a whole lot. But maybe somebody has ideas what's coming next. maybe we'll go with Meulen's little new molecules. That might be the next direction. I don't know. So let me leave it at that, and discussion.
How would you distinguish it, for example, from fluorescence, from hot luminescence or geminite recombination?
Yeah.
How do you know that it is Raman, or why do it's maybe terminological question, but why is it Raman, not fluorescence, if it all goes through real states?
Yeah, that is a good question, and it bothered us too. Time resolution is one thing. How you excite it. We have all these different processes with it. Initial, final state, and lifetimes. When we first saw this, and especially when for the monolayer and bilayer, and it's always resonant, that's troublesome. So you think that probably is fluorescent, but time resolved and intensity measurements are the way we usually do these kinds of things, and that's what we did.
You had a picture of these various interfaces, zigzag and so on.
Oh yeah, you want that back?
Yeah. I mean, do you
Oh,
have
you want
them-
the
you
one-
have them- That's right. And
No.
you seem to have,
I'll try to light them up.
yeah, that was nice.
I don't know.
Because you seem to have quite a high density of zigzag
Oh,
interfaces.
yeah, but that's because we have 20 layers. And what happens is that they break up on one layer and the next, and in this ordered way. We didn't expect that, but it always does that.
Right. I mean,
Maybe you have a theory for it.
no, not at all. But, I mean, there is this theory which has been mentioned that zigzag edge is ferromagnetic.
Yeah, but that wouldn't show up here. You have to do magnetic
Oh, I
measurements.
know,
too.
no, but I'm suggesting that if you could get a lot of edges, not just on the edge of ribbons, but in some more bulk
Well,
specimen. I mean,
your idea is-
ferromagnetic carbon.
Your
is
idea is
something
very
that
good.
we're looking for a long while.
The next step of your suggestion, I'm just taking your suggestion one step further, is you can make those edges like I showed here as part of a narrow ribbon, and the number of rows determines whether the relation of ferromagnetic and antiferromagnetic on the relative edges, and you might have very interesting magnetic array if you did that. That's the next step to your idea.
Yeah.
But you have to kind of arrange that. This sample isn't exactly right. You have to cut the sample
Oh, yeah.
to make the right shape so that we get exactly what you're talking about. But that's a great idea.
No, but I mean, there have been mentions in obscure places in the literature of carbon samples of various types of carbon where they claim they see ferromagnetism with very high Curie temperatures. Now, I mean, if you could,
I don't know how. They go up to 100 degrees. Or,
Well, I've seen there are a few odd. I mean, they may not be right, but there are a few in the literature where they've got much higher ones. Not in graphene or something. Various weird samples. But I mean, this would be very exciting if you could have something TC well above room temperature and something like that in carbon.
yeah.
You asked for something.
This is magnetic.
futuristic.
This is a TC for superconductivity.
Yeah, high TC ferromagnetism.
Yeah, right.
Exciting.
Yeah, it is. It's a good idea. Nobody had, but people have studied the magnetic features of the edges. The person that's done the most work on that is Inoki in Japan. If you want to follow that in the literature.
What determines the Raman shift of the peak in the electronic Raman scattering of your metallic nanotubes?
Oh, well, you could see that we have different Q vectors, so that's different energy required to go from the initial to the final state. So that's different wave vector and different energies. So that gives a very, very broad line, because that contribution is seen over many millivolts. It's not a very strong feature. We really have to work for a long time to get that spectrum. And that's why it's been missed all these years, because it's been seen, I'm sure, by many people, but they weren't looking for it.
I think you mentioned that you introduced acetonitrile, and there was another molecule to dope the nanotubes, and look, you showed the Raman Spectra for that. I wondered whether there was any signature of the dopant molecules themselves which come out or
yeah.
are enhanced by the nanotube.
Very good question. You have to work at that. When we were doing intercalation compounds, the one compound that we used to see very good spectra for the intercalant, that is the species that you put on, was bromine. I don't know why that one worked so much better, but there were other molecules like ferric chloride that we had a huge ton of data, and we never got the vibrations of that molecule. And I don't have a theoretical explanation why bromine is so wonderful, but bromine doesn't do stage 1, and I don't really understand that either. It only starts working on stage 2, and it's the only intercalant that I know that has that characteristic.
So I just wondered whether there might be
The shift is amazingly huge. The vibrational frequency goes from something like 300 to 200 wave numbers. I mean, that's almost unheard of shift in Raman spectroscopy.
There are some molecules where the adsorbed molecule Raman signature is very strongly enhanced by graphene.
Oh yeah, that's another thing I forgot to talk about.
Is there any connection between the nanotube work and the graphene work? Or?
Yes. Graphene is, it's called GERS. That's what you're referring to. There's a phenomenon called SERS, surface enhanced Raman scattering, which will enhance the signal of a molecule by many orders of magnitude, 10 orders of magnitude. It's a huge effect. With GERS, this is a graphene substrate. The enhancement is less than 1 order of magnitude, but it's very large. So that is to say, let me repeat, because maybe not everybody knows about this phenomenon. This is something pretty new. If you take a graphene surface and you put, say, a molecule sitting on the graphene surface, the spectrum of the Raman spectrum of the molecule will go way up in intensity. But it doesn't do it by many orders of magnitude. It does it by maybe a factor of a few. But that's a lot. So, I mean, it's very, very noticeable. And the work on that, the best, most complete work is done in Beijing. But anybody can do it. It's a very direct experiment.